So before I give you the answer for why the greatest gap occurs when the velocities are equal, I want you to have a look at this animation, and you might be able to figure it out for yourself. So have a look at this. It is sped up, by the way, so the numbers aren't going to make sense. I just sped it up so it doesn't last as long. So do you think you can see why? The actual reason for it is if we go from the start, well, this is the first way of thinking about it, which is just very wordy and based off this animation. See, at the start, the red one is moving very quickly, and because of that, it's getting further away from the blue one. And you can see this gap is increasing, but as the blue one gets faster, it's accelerating. You can see the gap is slowing down, as you can see down here. So the gap at the start, look how quickly it was increasing. But then once we get up to here, once the velocities are almost equal, you can see the gap starts to really slow down in terms of how quickly it's getting bigger. And the reason for that is that the blue is actually almost as fast as the red one, so the red one isn't getting away as quickly. And then once their velocities are equal at 25, you can see the gap goes up to 312, and then what happens is the blue one is faster than the red one, so that means it's actually going to start catching up to the red one, and the gap's going to start getting smaller, as you can see. So now after that explanation, if you didn't get it at the start, you might want to go back to the start, rewatch the animation, and see if that makes sense to you. But this is still pretty hard to understand because we have two objects moving at the same time and it's hard to visualize what's going on. So it might help if we actually look at it from another perspective where only one object is moving. One way you can go about it is by thinking about something called relative velocity. So as you can see, there's this car on the motorway, and it's obviously moving quite quickly, and the other cars are moving quite quickly as well. However, from our perspective, it looks like the other cars are moving really slowly. Like for example, that car on the right, that's moving away from us very slowly, even though we're both moving very quickly. And then as we'll see that black car on the far left, it looks like that car is moving towards us even though we're both going straight. It seems like that's actually moving towards us from our perspective. And this is called relative velocity, and we can do something similar with our little animation. So if we go back to our animation then, imagine the blue car is moving at 10 meters per second and the red one is moving at 25. From the blue car's perspective, how quickly do you think the red car seems to be moving from the blue car's perspective? Pause the video and have a quick think. Well, the answer is 15 meters per second, because if this is moving at 10 and this is moving at 25, from the blue one's perspective, it looks like this one's moving at 15. And the way that you calculate that is fairly straightforward. If you want the velocity of B relative to A, so it's relative to A, so that means that that's from A's perspective, so it's relative to A. It's the velocity of B minus the velocity of A, which in this case is equal to 25 minus 10, which is 15. Then if we were to do it from B's perspective, it would be a little different. We have velocity of A relative to B is VA minus VB, which would be 10 minus 25, which equal to minus 15, and these are both in meters per second. Why do you think it might be negative? Have a think about it. Pause the video. Well, the reason it's negative is because for the blue car, when the red one's moving faster, it looks like this one's moving away to the right. But for the red car, because the red car is moving faster, from the red car's perspective, it looks like A is moving to the left, and we'll see that in the animation in a second. So I've taken the animation from the beginning and I've fixed the position of the blue car, and as you can see from the blue car's perspective, so it seems like it's not moving, and then the red car seems like it is moving away. And then I made another animation which shows this more accurately with numbers. It shows the relative velocity with numbers. So what I've done for this one now is I've made the blue car not move, and I've made the red car move. So to find the red car's velocity, I did the red car's velocity minus the blue car's velocity, as I did in the calculation earlier, and I did that for the acceleration as well. So you got the relative acceleration and the relative velocity, and then I just plugged the numbers in, and this is what it looks like now. So basically, now it seems like, from blue's perspective, that red is moving away, but it's slowing down, right? So it's the same idea, except look, red is moving, and now look, it has negative velocity, and that means, so when it was positive, it was moving away from the blue one, so it was moving to the right relative to the blue one, but then when the sign switches, it starts moving towards the blue one. And what's actually happening here? Well, here, the blue one's actually moving faster than the red one, and because the blue one's moving faster, from blue's perspective, it looks like red is moving towards it. If you remember back to the car, when the other car in front is moving slower, then it looks like the car is moving towards us, and the same thing's happening here. You see we get the same numbers for the gap, 312, and it'll be the same time elapsed as well. So yeah, that's another way you can think about it. So another way you can look at it is by thinking about a velocity time graph. So ignore the black line, that's actually the gap as a function, and I'll get to that later. But if we just look at the red line, that's the red car's velocity, and the blue one's the blue car's velocity. If we want to find the gap, we can find the area under the curve and then subtract them, because the area under the curve gives you the displacement, and if you take them away, you'll find out what's the distance between them. by subtracting. So let's find the distance that the red car has traveled. Let's just say up until this point where the velocities are the same, which I'm doing for demonstration purposes to make the video shorter, but you can do it whenever. But I'm going to do it up to this point, and their velocities are the same after 25 seconds. So to find the area under the curve, and I'm going to write it in red, area equals, well, it's just going to be a rectangle. The height, as you can see, is 25, and so it goes up to 25 meters per second. It's always there, and then the length is 25, so it's just going to be 25 squared, which is equal to 625 meters. Okay, and now if we do that minus the blue area, so the blue area, the area equals, now it's a triangle with a height of 25 and a base of 25 too, so it's a half times 25 squared. Since it's a half times the base times the perpendicular height, and the base and the height are both 25. So basically the gap that means, so that'll give you whatever that is, 625 over 2. So that means that the gap is the difference. So it's 625 minus 625 over 2, which is equal to 625 over 2 meters. So that's how we can find the gap. And basically what we did here, if you think about what we did graphically, we took this red area, right? And we took away this blue area. So what we actually found was we found the area between the two curves. So we did the red one minus the blue one. That gives us the area in between the blue curves, which I can show you is here. Or the two curves. I don't know if I said blue curves. This pink area. Now let's just see what happens if we keep going. So we took the red one away from the blue one since the red one's in front. Let's keep going. And let's just go for like 5 seconds or something. So basically this 5 seconds later brings us to 30, for example. So if we get the area under the red line, I'll just go down again and I'll say area equals, you can see the width is 5, so it's a rectangle with a width of 5 and a height of 25. So 5 times 25, that'll give us 125 meters. And then if we do the blue area, well, it's going to be that rectangle, as you can see, plus this triangle. So it's going to be 125 plus, and then the triangle has a height of 5 and a base of 5. So it's plus a half times 5, which is a half times 5 squared, which is 25 over 2. Okay, and now if we do the same thing, we do the red area minus the blue area, look what happens. We'll have 125 minus 125 minus 25 over 2, which is equal to minus 25 over 2. Notice that this number is negative, and that's actually because the gap is decreasing. That's because the blue one's now moving faster than the red one, so that means once we get past this intersection here, because the blue line's above the red line, the area is technically speaking, the area between them for the gap is technically negative, which means the gap's getting smaller. So that means the biggest gap happens once all of this positive area, where the red's in front of the blue one, is filled, and not the blue one in front of the red one. So that means it has to be all the area up to this point, since after this it starts getting smaller. Another way we can think about it is with relative velocity, like I was saying earlier, we can actually graph that. So what if we graph the velocity of B relative to A, like I showed you in the previous animation, and we can actually graph that, and it's only one line, so it might be a bit easier. So you can see we do remember the velocity of B relative to A equals to velocity of B minus velocity of A. And B is the red line, and A is the blue one, we'll say here, because the B is in front. I'll make this black, sorry. There we go. So yeah, we can figure out the relative velocity. So at the start, you can see if we do the red one minus the blue one, it's 25 minus 0. So you can say the initial is 25. The initial relative velocity is 25, so you can start up here. And then as you can see, as this gets faster, we'll have 25, for example, here. 25 here, minus about 10 here. That'll give us a relative velocity of 15 after 10 seconds. So that would be about, so 10 seconds is here. And 15, sorry, it's still on black. 10 seconds is here. 15 would be 15 about here. So this point, and this is 10. And then obviously, if we have a look at when their velocities are the same, 25 minus 25 is just 0. So after, and that's at 25 seconds that happens just because of the numbers. That happens here. And you can see if we graph this, the relative velocity, it gives us a line, just a singular line like this. And if we find the area under this line, that's going to give us the gap as well. But notice that once we go under the x-axis, then the area is going to be negative because it's under the axis. So that means the gap's going to be decreasing once we get under here. So if we want to find the maximum gap, we want to find the area of this big triangle, which is up until their velocities are the same, or the relative velocity. So remember, this is the relative velocity of the velocity of B relative to A. And yeah, and of course when the relative velocity is negative, they're getting closer together. The area is negative, that means the distance is decreasing because the area is going to be negative, which means the gap's getting smaller. So the biggest gap is just the area under this positive triangle. Then a final way we can think about it is by thinking about the gap function itself. So as I said, this black line here is the gap function. So it's basically plotting the gap at every time. And as you can see, it clearly has a maximum, and we can find that maximum by using calculus. So think about how you could do that. I'd urge you to give it a go by yourself because it's not too difficult. Have you tried it? Okay, so basically, we can write the gap function, which you can call g, as the difference in their displacements. So since the red one's obviously going faster at the start, so it'll be in front, we can do the red displacement, SA, minus the blue displacement, which you can call SB. Okay, so that's basically what the gap is going to be. It's the difference in their positions. So for example, if SA is 120 meters along and SB is 40 meters along, that means the distance between them is 80 meters, 120 minus 40. So to find the maximum of a function, we can take its derivative and let it equal to 0. So I'd urge you to try that here and see what you can figure out. So take the derivative, let it equal to 0 to find the maximum, and see what happens. So if we take the derivative, and we're taking the derivative with respect to time, by the way, since time is on the x-axis. So if you didn't clock that, then you might want to try it again by yourself. So if we take the derivative with respect to time, we get dg dt equals, and then the time derivative of displacement is velocity. So we're actually just going to get VA minus VB. And then to find the maximum or the minimum, but clearly here it's a maximum, we can let that equal to 0. Okay? And now we have this equation, and if we bring VB to the other side, we find that the maximum gap happens when VA equals VB. And that's a pretty magical way of proving it as well. So yeah, there's 4 different ways of thinking about this. I'd urge you now to try numerical examples, see if using the numbers in the video. So I'll actually tell you the acceleration of the blue one is 1, and the initial velocity for the red one is 25 and it has no acceleration, and this has an initial velocity of 0. And I'd urge you to try to see if you can get the calculations, if you can get the numbers that happened in the simulation at the start, see if you can match them. It'd be very interesting.